In this section, I'm going to cover refraction and total internal reflection. I used mirage as an example because this optical phenomena illustrate both concepts very well. So imagine I'm driving on a road. Imagine I'm driving on a road on a very hot day, and this is the sky at a very far distance, close to infinity. And then the ray of the sky is gonna travel along this orange line towards my eye. And then I perceive light as straight line, so I followed the pink line and I saw the image is close to me on the ground. But in fact, the sky is very far away from me and it is not what I think it is. And I perceive the image of sky as water because probably I'm thirsty on a hot day. And the whole point about mirage is that when I get closer to here, let's say I'm here, I'm driving to here, a significant distance, I still see the image of sky. So I drive at the distance that I thought the image of sky were, but in fact, this time the image of sky is gonna move towards here, because the sky is still at close to infinity. So the mirage is like a fake image, and we're tricked. So the reason I mentioned about hot air is because when in a hot day, the light is gonna strike towards the ground. The ground is gonna be warmed, and then the lower layer, which closer to ground, is actually gonna be less dense because the molecule is gonna be separated apart when it is warmer. And so the air is gonna be less dense as the light ray travels from N1 all the way to N9. And in fact, the index of refraction, the value of it, is gonna be less and less also, and this is the trend I'm explaining. And N I refer as the index of refraction. What is index of refraction? We can look at the equation given here. V equals to c over n, where v is the velocity of light, c is the speed of light, which is 3 times 10 to the 8 meter per second, and n would be the index of refraction. And if we look closely, there's no velocity of light, or there's nothing that could pass the speed of light. So c is gonna be the maximum cap, the cap of velocity. So if we say c equals to v over n, then n must be something greater than 1.0. And 1.0 is actually the index of refraction of air in vacuum. So I define the index of refraction as the speed of light in that medium. And in our cases, the medium would be the air, the different layers of air. So to illustrate what mirage is actually happening, we're looking at two things: refraction over here from N1 to N7 or 8, and total internal refraction as air goes from N8 to N9. As we look at refraction, we always remember that angle is always measured from normal, which is this vertical line. So we're looking from N1 to N2, which is here. We're looking at this thing right here. So as light ray enters N1 to N2, it enters from a dense medium to a less dense medium, which means that N1 is greater than N2. Given by Snell's law, I forgot to mention what is theta I and what is theta R. Theta I is the incident angle, and theta R is the refraction angle, the angle of refraction. So this would be the incident ray, and this would be the refracted ray. So given by Snell's law, N1 sine theta I is equals to N2 sine theta R. And imagine that we're going in opposite direction from a denser medium to a less dense medium, so we're going backwards. It's just gonna be the same. And this time, the reflected ray is gonna be bending towards normal, so it's gonna be towards the normal, as theta I is, this time theta I would always be less than theta R when we're going from, if we're reversing, then theta I would be this angle, and theta R would be this angle. But we could see from here, like, I'm not gonna confuse with the notations. Because we could see from here, theta I is less than theta R. So we're looking at this angle is less than this angle. And that is what Snell's law tells us. So as we look into total internal reflection, we're looking at this portion, Na to N9. So what we have to bear in mind is that total internal reflection obeys whatever the law of reflection told us. And the law of reflection told us that this angle, theta of incident, would equals to theta of reflection. So the incident ray is gonna reflect it, and this would be the reflected ray. And how we could picture how total internal reflection is related to refraction is that, so as we can see, we're traveling from a dense medium to a less dense medium, right? So what if the incident ray is gonna be here? So probably it's not gonna be bent away from normal that much, so it's gonna be here, right? But what if this time we're looking at an incident ray that is closer to the boundary? So the refracted ray would be closer to the boundary as well. And as we go further, what happened is it's gonna reach to a critical angle that it refracts with a horizontal line along the boundary. And that is what we illustrate here. So we have an incident ray right here. This is the incident ray. And then the refracted ray is actually along the boundary. And this angle we measure as critical angle. And this could be seen from Snell's law, where right here I denote the two medium as n and n prime, where the value of n must be greater than n prime. So right here, n sine theta c equals to n prime sine 90 degrees because it is along the boundary. And we have theta c equals to sine -1 inverse, sine inverse of n prime over n. And this makes sense if we think like connecting these two together. It makes sense because if n prime is less than n, so this thing would be between 0 and 1, and the whole expression would make sense. It wouldn't be an error. So it would be a value that makes sense for theta c. So going back to the mirage example to illustrate how does the refraction and total internal reflection is occurring. So we always have to remember that in mirage, the air get less dense, and we're traveling from a denser medium to a less dense medium. So as the ray of sky travels from n1 to n2, this would be the normal, this would be the boundary. We have layers of air, just say it's horizontal. So this would be the incident ray, this would be the refracted ray. It's gonna bend away from normal. And then as we go from n2 to n3, we do the same thing, and it's gonna bend more because it's gonna be less dense. So it bends more here, same thing, to n4 to n3 to n4, and then to n5 to n6 to n7 to n8. So until it reaches, this would be going from n6 to n7, and this would be going from n7 to n8. I'm just drawing it approximately because I don't have a perfect diagram, because it's gonna be curved, and we're not looking at like 9 layers. We probably should be looking at 100 layers, where we divide the layers indefinitely. But just say like we're looking something close to this. So as we're going, this is going from n7 to n. No, we're going from n8 to n9. So this would be n8 and this would be n9. So as we're going from n7 to n8, this would be, let's say this is theta 7 and this would be theta 8. And we could see from n7 to n8 towards n8, there's refraction. And that means that theta 7 is less than theta c, the critical angle between n7 and n8. And then as we go from n8 to n9, we have total internal reflection. And we could conclude that theta 8 would be greater than theta c between these two boundaries. So as the light ray goes from n1 to n8, it's gonna be bending more and more until it reaches the angle that is greater than the critical angle between the two layers. It's gonna be reflected at that point, and the ray would be going upwards. And imagine if we're driving probably here, we're looking at here, then it's gonna pass through this layer and it's gonna bend again, it's gonna bend again, it's gonna bend again until it reaches to our eye. So this is mirage, and it illustrates both refraction and total internal reflection.